Let's have a look at optimization. That's in the chapter 12 of your textbook, section 12.3, maximum and minimum points and optimization. The previous video introduced this, and now we're going to have a look at optimization. Optimization. Many practical problems involve finding maximum or minimum values. For example, we may want to maximize an area or minimize cost. Such problems are called optimization problems. Let's go through example 9. A can of dog food contains 500 centimeters cubed of food. The manufacturer wants to receive the maximum profits by making sure that the surface area of the can has optimal dimensions. Let the radius of the can be r centimeters and the height h centimeters. Find the dimensions of the can that will have the minimum surface area. Now, we've got to ask ourselves, why do we need a minimum surface area? Well, if you've got a minimum surface area, it's less material to make the can, and if it's less material to make the can, then he can save money, and then he can maximize his profits. Okay, so as you recall from grade 8, the volume of a cylinder is pi r squared, that's the base, times the height. That's 500, because they told us it's 500 centimeters cubed. So we rearrange it to put h, and we've got h equals 500 on pi r squared. Okay, because the radius is r and the height is h. Now the surface area of a can is 2 pi r squared, that's the top and the bottom. That's pi r squared on the bottom and pi r squared on the top. We're talking about surface area. And the curved surface is the circumference of the top and the bottom, which is 2 pi r, times h. Okay, let's have a look at this. Okay, so this diagram should help. There's the can. So the radius is r, the height is h. Now, because we're talking about the surface area of a closed can, we have a bottom and we have the top. So that's the bottom, let's say, and that's the top. We know that the area of these circles is pi r squared. So we've got two of those, 2 pi r squared. Now this is unwrapped. This is the curved surface unwrapped. This distance right around the outside here is that length from there to there. And we know that the distance around the outside of a circle, the circumference, is 2 pi r. So we know that that's 2 pi r, that length. The height is the height. Okay, so that'll give us the area of the curved surface. Good, so the total surface area is going to be this plus that plus that. So it's pi r squared plus 2 pi r times h plus pi r squared. So that's why we've got 2 pi r h plus 2 pi r squared. Okay, next step. We already put h in terms of r. We got that from the volume formula. So we're going to substitute, where we've got an h here, we're going to substitute 500 divided by pi r squared. Okay, that stays the same, that one. So just that h, we're going to substitute with this. And then we're going to have the surface area in terms of the radius. And that comes out to be 1,000 over r plus 2 pi r squared. We now have s in terms of r. Now, remember what we said, when we want to differentiate this, which we need to do because this is a chapter on differential calculus, so differentiation, that's what optimization is. We need to move to this step. But before we can, we don't want to use fractions, algebraic fractions, in differentiation. So we want to move that to the top. So we're going to put 1,000 times r to the minus 1. And that's what we can see here. So this is exactly the same as that. This one down here is exactly what that is, but we have to put it in this form if we're going to differentiate it. Makes it a lot easier, right? Okay, so now what we're going to do is differentiate s with respect to r, ds dr. So remember, we bring the minus 1 down and we multiply by 1,000, so we've got minus 1,000. Minus 1, and we take a minus 1 away from that, so we got minus 2. That 2 comes down, then become 4 pi r with a 1 there. Okay, that's how we got to that. Then we have to equate this differential equation here to 0, because we know when we do that, it's going to be a maximum minimum point. And then we solve for r. Okay, so we put all that equal to 0, and we use the solver. You use the solve function in your calculator, and you find that r is 4.3 for that. And don't forget, you could read through all this. Well, let's quickly go that. In order to make maximum profits, the surface area of the can needs to be as small as possible. You are given the volume of the can, and you use this to find an expression for the height in terms of the radius. That's what we did there. This expression can be substituted into the formula for the surface area. Then you have an equation in terms of r only. So when you do optimization problems, you need two equations. You need this one, where in this case you need the volume, and then we've got the surface area, because both of them are using the same variables, h and r. Okay, and then you can then graph the function to find the local minimum maximum. Yeah, you could just graph that. That's a good idea. So you could graph this function here, not the derivative function, but the original function. You could graph that, or this is the same, and you can have a look on it and you can see where there's a minimum or a maximum. Okay, in this case, there will be a minimum. Okay, you can then graph the function to find the local minimum point, or you can find. Now, they've asked us the minimum surface area, so we can assume that there's going to be a minimum. Okay, it's in the question there, or you can use the derivative and just equate it to 0 that they've done here. So remember, once you get to this step here, you can just put the original function, which is either this one here or this one, into your graphic display calculator, and you can find the coordinate points of the minimum. And you can use analyze graph and you can find that point. Or you can equate the derivative function to 0, because that will give you the minimum point, and then you can find r at 4.3. Now it says here, check dsdr at r equals 4 and r equals 5. This is to confirm it's actually a minimum. Now if you've got the calculator and you can look at it on the graph, you don't need to do this step. Okay, it's a calculator question, so we're checking at 4 and 5 because we know if it's a minimum, the slope at 4 should be negative and the slope at 5 should be positive. Let's see, when we put r equals 4 in, we get the slope as negative. We put r equals 5 in, the slope is positive. The derivative goes from negative to positive, and so it's a minimum turning point. Therefore, the best dimensions for the can are radius r equals 4.3 centimeters. And how do we get height of 8.6? Well, we know its r is 4.3, so we just put r back into this equation here, and we can find what h is for that r. So when r is 4.3, we get h equals 8.6. And I just want to emphasize here, why did we choose 4 and 5? Because we got the r of 4.3, and we wanted to try a value just before 4.3, so we chose 4, and just after 4.3, so we chose 5. That's why we chose those two numbers. Let's have a look at investigation 5. Now, investigation 5 is very similar to the example that we just looked at, except this time, instead of a whole can, we've got half a can. Okay, that's just half a can, really, isn't it? It's a trough. Explain why troughs can be designed that have the same surface area but different volumes. Well, that's because we could change R and we can change H. So there's two variables we can change, okay? And that's why it says can be designed that they have the same surface area but different volumes. So as we increase R, for example, we could reduce H, and that would change the surface area of the part that's wrapped around there, but it would increase these ends. So we could keep a constant surface area, but the volume would be different. 2, find the formula for the outside surface area in terms of R and H. Okay. Well, the outside surface area of this is actually half of the outside area of the surface area of a can that we saw in the previous example. And so you should have pi r squared, right? It's basically that semicircle plus that semicircle is pi r squared. So that's half pi r squared, half pi r squared. So you add them together, pi r squared. And this height here, and the surface area of the curved area is now half of what it was for the previous example because it's half a can. And so we knew that previously it was 2 pi r times h. Well, it's 2 pi r times h divided by 2, which is pi r h. So the formula for the outside surface area in terms of r and h is now pi r squared plus pi r h. Now they told us that that equals 10 because they told us that the surface area equals 10 of the trough. 3, as you increase r, describe what must happen to h to keep the surface area at 10 meters squared. Well, as you increase r, as we said, you'd have to reduce h, the height, to keep the surface area the same at 10. Does the volume of the trough increase as r increases? Well, the volume would increase. If you increased r and you kept h the same, the volume would increase. But then the surface area would also increase. We're limited here to a surface area of 10 square meters. Describe what happens to the volume. Okay. 4, rearrange your formula from part 2 to make h the subject. Okay, in here we had that pi r squared plus pi r h equals 10, and we rearrange that and it becomes h equals 10 minus pi r squared divided by pi r. So just have a look at the previous example and you can do the same here and just write it in. 5, find the formula for the volume of the trough. Why can you not find the maximum volume of the trough yet? Because the formula for the volume of the trough, as we saw, would be half of what the formula was for the can. So we remembered what that formula was, and that was pi r squared h, right, for the whole can. Well, the formula for the trough, the volume of this trough, wouldn't be pi r squared h because we've only got half of it. So it's pi r squared h divided by 2, or 0.5 pi r squared h. And it says, why can you not find the maximum volume of the trough yet? Well, we've got two variables. We've still got r and h, a volume in terms of r and h. 6, Substitute your expression for h from 4 to show that volume equals 5r minus a half pi r cubed. So this says from 4. Well, in 4 we rearranged it and we said that h equals 10 minus pi r squared all divided by pi r. That's h. Now we substitute that into the formula for the volume, and the volume was 0.5 pi r squared h. So that becomes 0.5 pi r squared, and h we replace with 10 minus pi r squared all divided by pi r, and then we get this equation here, which is the volume equals 5r minus a half pi r cubed. Then it says draw a sketch or use your GDC to plot the graph, so we can just plot that directly in our GDC, and we can see that there is going to be a maximum just looking at the graph. 8, how do you know that the trough has a maximum volume? Well, you can have a look at the graph and there's a maximum point, okay? And how does the maximum value relate to that? Okay, the maximum value is where the function is maximum. And we have to find out what value of r gives that function the maximum value, okay? And we can do that on the graph. Just use analyze graph and you can find that point. You can find the value of r. Just use the analyze graph and maximum. 9, find the derivative of this function and solve for 0. This is another way you can do it. If you didn't want to use the GDC, you just equate that to 0 because we know this is going to give us the maximum point. What does your solution represent? It represents a turning point, either a maximum or minimum. We know it's a maximum from the nature of the question. Find the maximum volume of the trough. Well, if you want to find the maximum volume, we found R through here, and then so you just put R back into this equation, you can find the maximum volume. Okay, 11, explain how you can check that it is indeed the maximum value. Well, you could look at the calculator and you can see that it's a maximum value, or you could go back to your derivative function that we had, and our derivative function was 5 minus 1.5 pi r squared. That's the derivative of that. Okay, and we solved for r, and we got a value of 3.43. Now, is that point a maximum or a minimum? We know the slope of the gradient at that point is 0, but do we know if it's a maximum or minimum if we didn't have the calculator and we didn't plot it? Okay, so when we did solve the derivative, when we equated that to 0, the derivative function, we found that r, to satisfy that, r had to be 3.43. So what we need to do is we need to substitute into the derivative function something less than 3.43 and something more than 3.43. So we put in a 3 and we find out that it's positive, and we put in a 4 and we find out it's negative. Therefore, it would be a maximum, because remember, when the gradient changes from positive to negative, the stationary point is a maximum. It says find the maximum volume. To find the maximum volume, we just put r back into this equation here. Explain how you can check that it is indeed the maximum, and we've just talked about that. How does finding the maximum and minimum values help in solving real-life problems? Well, there's an example, and this is very good down here as well. If a function to be optimized has only one variable, then either a graphic display calculator or differentiation can be used directly to find the maximum and minimum point. If a function to be optimized has more than one variable, like we see we've got an r and an h here, then a constraint must also be given. This constraint can then be written as an equation and substituted into the function to eliminate one of the variables. That's what we did. We had two equations. We had our volume equation and we had our surface area equation. And we had the two variables h and r. And exercise 12F, you can have a look at another video that shows the solutions to this. Question 1, question 2, 3, 4, and 5, and questions 6, 7, and 8.